Shimon Kolkowitz. It's even more pleasant that you're down here not just as the colloquial speaker, but as a faculty member. So let me say a few words about Shimon. Shimon graduated with work on nitrogen vacancies in Diamond at Harvard University. Went on to do a postdoc with building atomic clocks. And the history of the atomic clock and the history of atomic physics are really intertwined. Every important step forward in an atomic clocks has also been an important step forward for atomic physics in general. All this work usually happened at national metrology labs. Those are NIST, the National Institute of Standards and Technology in the US, or the Physikalisch-Technische Bundesanstalt, PTB in Germany. Those are the institutes tasked with maintaining the units of the international system of units. And they have the long-term vision that is really necessary to improve the long-term stability and the accuracy of clocks. Along comes Shimon and asks a couple of very powerful questions. Atomic clocks have always been built with the goal of better timekeeping, better navigation, where you need to compare the clock to events in the outside world. But they have also doubled as instruments for precision tests of the fundamental laws of physics. What if I build a clock with the main purpose of testing fundamental laws of physics? What systematic effects can I cancel if I optimize two clocks for the purpose of comparing them with one another rather than with the outside world? How much more accurate can I get by that? And I'm looking forward to hearing the answers in your talk. Welcome, Shimon.
Introduction. I have to say, you kind of gave about half my talk for me, but much briefer. I also want to say thanks to everybody for coming to the Kolkowitz, but also, as most of you know, I think I just started here at Berkeley as faculty just a few months ago, and I just wanted to thank the whole Berkeley physics community for the warm welcome. I just think it's really, the transition has been very seamless and smooth, and it's really, I'm very happy to be here. And it's a pleasure to have the honor of giving the physics colloquium today. So I do also want to say that I hope to keep this pretty informal. I also strongly encourage the students in my Physics 5A course to attend, and I see a lot of them in the audience, so thank you for being here. But as a result, I know that some of the concepts, I try to keep it at a level that should be understandable to undergraduate physics majors and grad students and faculty in other areas of physics. Please ask questions if anything's unclear. Just speak up. Okay, so as Volker said, I want to tell you a bit about testing relativity in the lab with ultra-precise atomic clocks. And so here's the outline. I want to tell you about, first of all, just give an introduction to clocks in general. And I completely agree with Volker that not only has, I think, atomic physics kind of progressed hand in hand with atomic clocks, but I would kind of claim that physics has progressed hand in hand with clocks. As we've developed better clocks, it's given us access to understand and study entirely new physics. In fact, I used to give a colloquium where I gave a whole history of the development of the clock, and I tried to make points about how physics developed along with it. I'm not going to do that today because there's a lot of interesting results that I want to tell you about, and I used to do that before I had results to talk about. But I do think that that's still really true. So I'm going to tell you an introduction to clocks. I'm going to talk a little bit about a little bit of history, just a little bit of test of relativity with clocks. And then I'll tell you about exactly what Volker motivated already, which is a new kind of clock that we have developed in my group with the express purpose of using it to study physics, fundamental physics, and to search for new physics, and in particular for the purposes of this talk, to test relativity. And I'll tell you about our recent results in that direction. Okay, so first of all, we're going to talk about clocks. We have to say, what is a clock? Okay, and I would say most of us, when we think of a clock, we can just go outside. Right outside this lecture hall, and we can look up at the campanile, and that's kind of what we think of as a clock. But of course, that doesn't really answer the question, and in fact, the thing that we think of as a clock is really just a counter that's counting the oscillations of a local oscillator. And the local oscillator and this is clock terminology, is really the thing that's the actual clock. And so the quintessential example, the very first modern clock was the Huygens pendulum clock, and it's just a pendulum. And because that's a simple harmonic oscillator, at least for small angle, in small angle approximation, this has a very reliable frequency that doesn't depend on the amplitude of the motion. Everybody in my 5A class is getting a little nervous that I'm going to quiz them about the pendulum or something like that. I'm not going to ask any pop quizzes today. But you're all familiar with it, and you know that the period, actually one of the nice features of the pendulum is it only depends on the length of the pendulum and on the acceleration due to gravity, not on the amplitude of the oscillations or on the mass of the pendulum. So if a piece of dust settles on here, it shouldn't really change the frequency of the oscillator at all. And so that makes it a very nice clock. And then actually we use something called an escapement, a mechanical escapement, to convert that ticking and count it and convert it into the ticking of the hands on the clock. Okay, that's not really how most of the clocks work. Most clocks work anymore. And to be honest with you, I don't know how the clock in the Campanile works. I spent a bit of time Googling it and was able to figure it out. But modern clocks, like the ones in your cell phones and in your laptops and things, rely on a piezoelectric tuning fork made out of quartz. It looks something like this. There's different versions of it. They have different shapes, but they all kind of behave pretty similarly. So this is just a tuning fork. It just vibrates at a very specific frequency. And because quartz is piezoelectric, you can measure that frequency electrically, and you can count this and use that to keep track of time, and then put that on the front face of the Campanile. And this is actually what's in your wristwatch and your iPhone and your microwave and everything like that. So we can now ask the question, okay, that's how a clock works. How good is our clock? Okay? And if you just have the Campanile and nothing to compare it to, that's a hard question to answer, because the best you can do is just look at it every day and see if it seems to agree with when the sun is rising and setting, and it's kind of hard to say, and especially on a day like today, just a couple days after daylight savings time has ended, that might be kind of confusing. But if you want to actually know how good a clock is, what you could do is you could build two Campaniles, and you could compare them to each other, right? And so you could start them synchronized and wait some amount of time. You might come back a few days later, and you might notice that now one of them is at a different time than the other one, right? And so now you kind of have an intuitive sense of how to define how good a clock is. If these two identical Campaniles agree with each other over a longer period of time, that's a better clock, right? So the longer it takes for them to drift off with respect to each other, the better the clock is. And in fact, the way we parameterize how good a clock is we divide how long it took that clock to get off by a second by the number of seconds it took to get off, right? So 1 second. Now, I'll give an example, concrete example in a minute. Now, another interesting question is which clock is correct? And that's not really well defined when you just have two clocks. You only can compare them to each other, and unless you know one of the clocks is better than the other one, you're not sure which one is right. So if you built three Campaniles, then you could actually do what's called a three-cornered hat comparison, and notice that two of them seem to agree better than the other one, and then you can isolate that this one is probably the worst clock, and figure out how they're each shifting around with respect to each other. This also gives you some sense that in general, when you're talking about clocks and time, the best thing you can compare to is another even better clock. So now to give you some concrete sense, the quartz oscillators in your iPhones, if your iPhone wasn't connected to the internet, you would notice that it would start to drift with respect to the other clocks, like the front face of the Campanile or the clock on your microwave oven. And in fact, that's due to a couple of different factors. One is that this frequency depends on the shape of this tuning fork, and if the temperature changes, then because of the coefficient of thermal expansion of quartz, that shape will change and the frequency will shift. But also actually quartz actually ages. And so you get this kind of reliable trend over time where the frequency drifts. And this is also happening in all of the little tuning forks in all of our modern devices. And then, of course, every tuning fork you make is slightly different from every other tuning fork. And so everybody's clocks are all drifting with respect to each other. And for these kinds of clocks, the fractional frequency uncertainty, which again is the number of seconds it takes to get off by 1 second and then inverted, so that's 1 times 10 to the minus 6. That's the relevant sort of figure of merit for these quartz oscillators. That means there's about 3 times 10 to the 6 seconds in a month, and so these kind of clocks are precise to 3 seconds in a month, or so, give or take. And this is why over the course of a few months or many months, you might notice that your microwave gets faster by 1 minute with respect to your phone, which is constantly talking to the internet and correcting these kind of tricks. Okay, so what can we do about this? This is fine, if we just want to meet up or to know when we started the colloquium, etc. But of course, if we want to do science, we want to do better than this. And so that motivates the idea of an atomic clock. And an atomic clock actually works exactly the same way. We still have one of these local oscillators. It's still just some mechanical tune fork or something like it. But now what we do is we take the frequency of that local oscillator and we compare it to the transition inside of an atom. And we pick a very specific transition. We typically use the hyperfine transitions in hydrogen-like atoms, like hydrogen or rubidium or cesium. They're all in the first column of the periodic table. And we pick a hyperfine transition where that transition is very well isolated from the surrounding environment. It's a very narrow transition. And we take this frequency, we multiply it up until we think it's on resonance with this transition. When we shine that radiation, we hope on resonance with the atom, after preparing that atom in one state, in the ground state here of this transition. And when we shine the radiation on it, if we're on resonance, the atom gets excited. But if we repeat that experiment after our oscillator has drifted away, nothing happens and it stays in the ground state. So just by sitting on the edge of this transition and feeding back to keep our local oscillator tuned so that we're always excited, say, half of the atoms, we can feed back and correct for all of the drifts of our local oscillator because the temperature changed, because the quartz is aging, because the local oscillators were different, and because every cesium atom is identical to every other cesium atom as long as we prepare it in the same environment. Now we can all agree on the time and we can do physics together, right? We can ask how good of a clock can you make now that you can use this feedback mechanism. And the thing you can notice is when you measure your atom, you never measure it in this combination of G and E, which is quantum mechanics we call superposition. Instead, when you measure it at the end, you project it into either E or G. And if you're sitting on the edge of that transition where there's a 50-50 chance, this is just a little quantum coin flip that you perform with each of your atoms. And so there's noise associated with that probabilistic measurement. It's just a 50-50 chance every time of measuring each of the atoms in E or G. And that creates something called quantum projection noise. And you can very easily write down an equation that tells you exactly how good your clock is, and it only depends on a few things. It depends on the frequency of the transition, it depends on how many atoms you're measuring, it depends on the dead time between each measurement, which is this TB, and it depends how long you compare your local oscillator to your atoms for, and I'll come back to that later in the talk. And then finally, it just depends on how long you actually measured for, and that's this tau count here, which is the total measurement time. And so using this equation, we actually have a formula or a recipe for making better and better clocks. And you can see that since the invention of atomic clocks, this fractional frequency uncertainty that I already motivated or explained has gotten better very rapidly, about a factor of 10 every 9 years or so, from the 1950s until the early 2000s, until these microwave clocks got to the level of accuracy and precision of about 1 second in 300 million years. So now if you build two campaniles with these atomic clocks in them, they agree on the time after 300 million years to better than 1 second, which is pretty amazing. And that's enabled all kinds of really important applications of these clocks. So in particular, one that we probably all take for granted, but that we use pretty much every day of our lives, is the GPS network. The GPS network actually relies on a number of satellites, each of which has one of these atomic clocks inside of the satellite, and they're just constantly broadcasting where they are and what time it is. And your phone uses that information to triangulate with respect to those satellites because of the finite travel time of the signals from each of the satellites because of the speed of light. You can figure out exactly where you are on the surface of the Earth. Maybe more importantly for this audience, we've now gotten so good at making clocks that we can measure time or frequency better than we can measure any other unit or anything else with units. So recently, we actually redefined the SI unit. Holger already kind of referenced this, to this new system, this new SI, which was adopted in 2018, where you can see all units are defined with respect to fundamental constants, which are actually just numbers that we write down, and the second, which is referenced to the hyperfine transition of cesium. So now, the extent to which we can measure anything with units is determined by how good of a clock we can make. And that motivates making better and better clocks. So how can we make an even better clock? It turns out that this 1 second in 300 million years I told you about is about as good as we can do with hyperfine transitions or microwave transitions. Those kind of clocks based on cesium and rubidium have basically bottomed out. We don't know how to make better ones. But we can look at this equation and notice that there's a parameter here that we're kind of stuck with if we're using hyperfine transitions, which is the frequency of the transition. If it's a hyperfine transition in neutral atoms, that's typically on the order of 1 gigahertz to 10 gigahertz. We can choose to move from a hyperfine transition to a transition between orbitals of the electron and an optical transition. And in principle, if you go from microwave transitions to optical transitions, that's a factor of 10 to the 5 that you can potentially get an enhancement in clock performance. And so you have to move to a slightly more complex atom to do this. We go from these very simple hydrogen-like atoms with only one valence electron, to slightly more complicated atoms like strontium or ytterbium that have two valence electrons, and that gives us access to very narrow optical transitions. The other thing that we have to do is we have to change what our local oscillator is. Before, our local oscillator was just this quartz tuning fork that we could multiply up to microwave frequencies. Now we need something, a local oscillator at an optical frequency, and we can't really multiply frequencies up all the way up into the optical part of the spectrum. And we also don't have electronics to count frequencies at hundreds of terahertz. So instead, actually, our local oscillator is now a laser. That is actually just a local oscillator at optical frequencies. That's really what a laser is. It's a shame that now I use, digital laser pointer. I would tell you that that spot was actually a clock, okay? But if this was, imagine this was a laser pointer, and then that would be a not very good clock, but it would be a clock. But the thing is, you need some way of counting the optical frequencies, and that is something called the laser frequency cone, or an optical frequency cone. That was actually the 2005 Nobel Prize that mentioned Jan Hall. And basically, you can think about that as a way, a kind of reducer, a gear reducer, if you want, to reduce optical frequencies down to microwave frequencies without losing any of the precision or accuracy. It's really an amazing, invention. I'm not going to talk any more about it, but you're welcome to ask about it if you'd like. And so that now allows us to take advantage of these slightly more complicated atoms with two valence electrons, and to take advantage of transitions like this one, which is an intercombination line between the singlet ground state of strontium and this triplet P0 state. And that transition is a 1 millihertz line width transition at hundreds of terahertz, 429 terahertz, and that gives a natural quality factor of this transition of 10 to the 18, which is really, truly remarkable, and this is really what enables us to make really precise plots. Of course, to take advantage of such a narrow transition, we now have to worry about new things that weren't such a big problem with the microwave clocks. In particular, I'm losing my laser pointer here. In particular, you have to worry now about Doppler shifts of light. So at microwave frequencies, Doppler shifts, which scale with the frequency of the light, are not so big, and you typically don't have to worry about them. But with optical frequencies, they're 10 to the 5 times bigger. And so we need very, very cold atoms. So we start with atoms that come out of our oven. When we take a piece of strontium and heat it up, they come out at 800 Kelvin. We laser cool them down to 2 millikelvin, or 2,000th of a degree above absolute zero. Okay? This is what they actually look like when we do that. So that little blue ball that's glowing there is a cloud of about 1 billion or so strontium atoms that's being held in what's called the magneto-optical trap. And they're at just 2,000th of a degree above absolute zero or so. It turns out that's not nearly cold enough, so we do another stage of laser cooling on a second, even narrower, narrow optical transition. This is a single laser transition. That gets us down to 2 microkelvin, which is 2 millionths of a degree above absolute zero. That's still not nearly cold enough. We're trying to take advantage of a 1 millihertz line width, and the Doppler shifts for this temperature would still be 40 kilohertz. So we need some other trick. And our solution is actually to tightly confine the atoms, to hold them tightly in place with light. And this is what's known as an optical lattice. And so you can picture our experiments as 2 counterpropagating laser beams that interfere to form a standing wave. Okay? Because they're focused, these atoms are high field seekers. We pick a frequency of the light that we use to hold them where the atoms want to sit at a field maxima. Because we send the lasers from 2 different directions, that forms a standing wave. Okay? And then because it's focused, the atoms want to sit at that focus. And so you can actually think about our trap as a stack of pancakes, and the atoms are like the blueberries in your stack of pancakes. And what we do is, because we hold them strongly enough relative to their temperature and the recoil frequency of these atoms, which I won't go into, the motion of these atoms along this strongly confined axis, or along the corrugation of this lattice, becomes quantized. And now we can actually separate out the internal transitions of these atoms from their motion. This is what that actually looks like. So this is data that I took during my postdoc in June's group. You can see that if we don't strongly confine the atoms, you just get this Doppler rod and line shape. As you start to turn on this lattice and this corrugation, you get these kind of very funky features that actually most of my research as a postdoc was devoted to studying this kind of behavior, because this actually is a nice simulation of similar behavior to electrons moving around in a lattice. Okay? But we go into the strongly confined regime where the electrons basically, or where the atoms are no longer free to really move, and they're very strongly confined. And then you can see that now we get this very narrow clock transition that we can actually take advantage of. There's a price to be paid for this. By holding the atoms strongly in place, we're actually shifting the energy levels of the atoms around with that light. That's how we hold them in place with the light. And that's terrible for a clock, because we really want to measure a very specific frequency, and now we're strongly perturbing that frequency with the light. But fortunately, there's a trick. It's what's known as a magic wavelength. That's actually the term of art in the field. And that corresponds to this happy coincidence where the polarizabilities, where the shifts with respect to the intensity of the light, cross for the ground state and the excited state of the spot transition. So both energies are moving around the lot, but they're moving around together. So that at exactly this wavelength of the lattice, you don't get any shifts of the spot transition, and it's independent now of the intensity of the lattice. Things like that. And this is data from one of our recent papers where you can actually see that in action. You can see that we have to be at exactly this magic wavelength where we start to lose contrast of our Ramsey fringes, which we'll talk about in a minute. So now we have these optical clocks. These have improved even more rapidly than the microwave clocks I already told you about. They've improved by a factor of 10 every 3 years or so since the laser frequency cone was first invented in the early 2000s. And we're now at a level of accuracy and precision of 1 second in 14 billion years. 1 second, better than 1 second in the age of the universe. So you could build two Campaniles at the Big Bang and keep them ticking until now, and they would agree to with each other to better than 1 second on the age of the universe after 14 billion years, which is really pretty amazing. And now I do want to mention that there's other important figures of merit for clock performance that I haven't really talked about. I've been using this one number. This is something the community typically does. But actually, there's a couple of different things. There's the statistical uncertainty that comes from that equation that I already showed you. And actually, as I showed you in that equation, the uncertainty scales with square root of 1 over square root of the averaging time. So as you measure for longer, as you compare your local oscillator to your clock for longer to this internal atomic transition for longer and longer, you measure time better and better. And you can see that averaging down with square root of the averaging time here. And this Allen deviation that you can see, this is just a way to basically measure this statistical, what we call stability or precision, which we're measuring the transition. And so, so that's just going down, and if you average for long enough, here you can see that in this very nice paper from June Yee's group before I joined the group, where they did a clock comparison between two of these clocks, it averaged down at 3.4 times 10 to the minus 16 per root hertz. So if they averaged for about 10 to the 4, 10 to the 5 seconds, they could get down to this few times 10 to the minus 18 regime. But of course, that just tells you the statistical uncertainty. You also have to worry about the systematic uncertainty. Or in other words, is there anything else that could shift these atomic energy levels around? Because I want to build two clocks and make sure that they're identical and that the atoms are in the exact environment. And it turns out there's a lot of things that can shift around these energy levels on the level that we care about. So you have to characterize all of these systematics, and they did that very carefully, and they got down to a statistical or a systematic uncertainty of 2 times 10 to the minus 18 in this paper. And that combined with your statistical uncertainty is what lets you say that this clock is operating at this 2 times 10 to the minus 18 or 1 times 10 to the minus 18 level. And this level of precision and accuracy has given rise to a whole bunch of new applications. Holger mentioned, for example, some of the things that we've been thinking about and that I'm very interested in, and including things like using these clocks for gravitational wave detection, searches for new physics, and today I'm going to tell you about using it for tests of relativity. Okay, so why do tests of relativity, and in particular, why do tests of relativity with these clocks and in the lab? So relativity and quantum mechanics, I would say, are two of the most successful theories that we have in physics. They're both examples of modern physics. They both came in large part from the same person, and they've both been around for about 100 years or so, and they're remarkably successful. Right? Relativity has successfully predicted, for example, the recent detection by LIGO of gravitational waves, these truly cataclysmic events where you had two black holes, both many times the mass of the sun, tens of masses of the sun, moving around each other at relativistic speeds, close to the speed of light, and merging into one black hole and radiating out more energy as gravitational waves than all the stars in the universe are radiating as light. Right? And yet, it still perfectly matches the predictions of Einstein's theory of general relativity. At the same time, quantum mechanics we're using in our lab every day to try to make amazing sensors, as Holger is doing, or quantum computers, as Hartman and Dan are working on doing. And this really predicts the structure of all of the atoms on the periodic table. Quantum mechanics is also very reliable. We've yet to prove it wrong. And yet we don't know exactly how to fit these two theories together, and we don't know how they work together at their interfaces. And in fact, there's a lot of work on the theories of quantum gravity and understanding, for example, what happens to quantum information as it vaults into a black hole. There's this black hole information paradox. But also there's questions of basically, what happens when you have these quantum mechanical systems interacting with effects of relativity. And I think this is a really interesting, rich space to play in. And it motivates doing tests of relativity in the lab with quantum systems. So what are we going to test? Specifically, we're going to test this prediction of general relativity known as the gravitational redshift or gravitational time dilation. And what this corresponds to is because of the force of gravity or the Earth's gravitational field at the surface of the Earth, if you raise one clock up with respect to another clock, it will tick faster than an otherwise identical lower clock. Okay? And for the strength of Earth's gravity or the acceleration of the gravity at the surface of the Earth, for sort of small changes in height, you can very simply write down what the scaling will be, and it's just the acceleration due to gravity times the difference in height divided by the speed of light squared. And what that gives you for 1 meter height difference is a fractional frequency difference between these two clocks of 1 times 10 to the minus 16. So with these very precise clocks now, we have the ability to measure these effects in the lab at the meter scale. This was first demonstrated in this beautiful experiment by Pound and Repka in 1960s and 1964 with using Mossbauer spectroscopy at Harvard between a source and an absorber that were separated by 22 meters. And this was a really remarkable triumph and one of the first experimental validations of the theory of general relativity. I really like, you can actually see, there's this nice article about this from Horowitz, Paul Horowitz, and he shows an actual scan of Pound's original notebook, where you can see he sort of circled his result or plots his result, just like you might in your own lab notebooks for an undergraduate lab quiz, and you can see that the result for the redshift is consistent with the Einstein value. Okay, but I sort of said we want to test this with clocks. Mossbauer spectroscopy is not exactly clocks because we have no idea what the frequency of the radiation that's being emitted or absorbed is. We're just looking at absorption and emission using this, these kind of same source and absorber. So we like to do this with clocks, and to measure a 10 to the minus 16 effect for a meter is very hard, but one thing you can do is increase that difference in height. So on Gravity Probe A, they put a hydrogen maser on a rocket, and they launched that rocket up and compared it to a hydrogen maser on the ground, and indeed they were able to observe this effect quite significantly with many sigma, and this was for many years the most stringent limit on sort of modifications to the gravitational redshift, or what's called local position invariance. Okay, but now that clocks have gotten so good, we can start to do the same kind of experiments in the lab. And there was a beautiful experiment from NIST in 2010 where they raised one optical clock up a foot with respect to the other one. And they could see that the effect of this gravitational redshift, or the time dilation, just from lifting one clock a foot with respect to the other. So if you think about it, this means that because you spend most of your time upright, your head is actually slightly older than your feet. You can do the math, and if you live to be 100 and you spend half your time on your standing upright and you're 2 meters tall, it's about 300 nanoseconds or so over the course of your life. Which is not a big effect, but it's also an effect that we actually can measure, right? And that's what these kind of experiments are actually showing. We're just entering this really interesting but somewhat frustrating regime where these clocks have gotten so good that you're now sensitive to centimeter scale changes in height. That's pretty cool, but it's also very troubling because as we make these clocks better and better and we want to compare them to each other, we now have to know their relative heights to better than 1 centimeter. And actually, there's not a good way to do that over long baselines anymore, to know the height with respect to Earth's gravitational potential. And so this is kind of bad news for doing clock comparisons between standards institutes and using different kinds of clocks. But it also, we can turn that bug on its head and turn it into a feature, as people are starting to do, and start to use these to measure Earth's gravity and altitudes on the surface of the Earth using these clocks, because now they can measure it better than anything else can. And so this is an emerging field known as relativistic geodesy, where people are just starting to do sort of demonstrations. The real challenge with these experiments is to make these clocks portable and mobile, and reliable enough so that you can compare them side by side and then take one of these clocks somewhere else and still rely on the fact that its frequency hasn't changed aside from these gravitational effects or this relativistic effects. Okay, another reason I think this is a really interesting regime to be entering into is, as I already motivated, we can do, and Olger does this on a regular basis in his lab, we can make superpositions of atoms being in multiple places at the same time on the scales that we're now starting to see the effects of relativity show up. So you can imagine, and people have proposed these kinds of thought experiments, where you take one of these atoms that's in an internal superposition, and you also put it in a spatial superposition of being at two different heights at the same time, and then you try to interfere it with itself. And what you find is that because there's a gravitational redshift or a gravitational time dilation and a difference in potential energy between these two heights, you'll actually see a drop in the visibility fringes of the interference of these matter waves when you try to recombine them because of the effects of relativity. And this is kind of the thought experiment that hasn't been tested in the lab, and I'll return to this at the end of my talk, but I think this is a really interesting kind of step in the direction of thinking about how relativity and quantum mechanics actually interact with each other. Okay, so here's where we are, and this is where I want to play around in the lab and actually do these kinds of tests. So we built the clock with that in mind, and here is our strontium 87 atoms in our optical lattice. Here is this commercial clock laser that we bought. It's a very nice narrow line width laser with about a Hertz line width, so this is great for doing these measurements. Now there's one more thing I have to tell you about, which is how we actually do these measurements. We do these measurements not using the kind of standard absorption spectroscopy that I told you about before, but rather something called Ramsey spectroscopy. This is a perfect example of what Holger said in his introduction about how atomic physics and clocks have really gone hand in hand. Things that were originally developed for NMR, but then became used for atomic clocks and are now the workhorse of basic atomic physics experiments. So the idea is, rather than sort of sweeping across the frequency of this transition, we start with our atoms in the ground state. We apply what's called a pi/2 pulse, which just means we create a coherent superposition of these two states. We allow that superposition to evolve for some amount of time, and then we do another on-resonance pulse on the same transition, and the outcome basically converts the population in these two states into a measure of the phase difference that was accumulated between the superposition that you created and the phase of your local oscillator that was evolving in time. And so using this, you can actually measure the detuning between your local oscillator and this internal atomic transition. And here's a beautiful example. This is actual data from one of these atomic fountains on a cesium microwave transition. So that is actually the sinusoidal dependence on the atomic of the atomic population on the frequency difference between the microwaves that they were shining on these atoms and the internal atomic transition frequency. And so you can use this now to measure that frequency very, very precisely. So we're going to do the same thing. So you can see we can use our clock laser now to probe this optical frequency. And then you can see that over time, our fringes, our Ramsey fringes, this sinusoidal fringe that we'd like to measure, is decaying. And what's actually happening here is that we're losing track of the phase, not of the atoms, but of the local oscillator, of the clock laser. Basically, we bought a very fancy laser, but it's still not fancy enough for us. And so after just a few hundred milliseconds, we kind of lost track of what that local oscillator was doing in this time because it's random from shot to shot. And this is a big problem for us because it limits the stability of our clock to something like 6 × 10⁻15 per square root hertz. This is the best that we've managed to measure with our clock. That's not too shabby for an optical clock. It's not state of the art, but it's pretty good for a clock, okay? But then you can say, well, I told you I wanted to measure a millimeter redshift or so. How long would it take me to measure 1 millimeter redshift with this stability? It would take 114 years of averaging. Okay? And I don't think I can convince my grad students to do that experiment. And what's even more troubling is that to do one measurement of the redshift at 1 millimeter, it doesn't include systematics at all, right? And so, we actually spend more of our time characterizing systematics than we do actually measuring the thing that we need to measure. So this is really problematic and we need some tricks. And so we actually turned to inspiration to some of the experiments that have come out of groups like Holger's group here, where they do differential comparisons between two atom interferometers in order to measure the fine structure constant, or LIGO, where they want to measure very, very, very small differences in arm length between these two arms, and they would actually be limited by the frequency fluctuations of their laser that they're trying to do this, except for they make a Michelson interferometer with two arms, and that frequency noise exactly cancels when those arms are equal length, and as a result, they're able to measure the arm length difference much, much more precisely. And so we're going to do exactly the same thing with this new kind of optical clock. In particular, we're not going to make one clock, we're going to make two or more clocks in a single optical lattice. This is what this actually looks like in practice. So here you can see us loading one region of the lattice with these ultra-cold strontium atoms, shifting them over, and then loading another region, In a second, you'll see we'll turn off the magnetic optical trap and the remaining atoms that weren't trapped will fall. And then now we shift back over and we have these two plots that we can do a simultaneous comparison between them. So if we try to probe for much longer than the coherence time of our local oscillator, you can see here we went out to 8 seconds. The phase of the second pi over 2 pulse with this laser is completely random, so we just repeat the same experiment and we just get other noise. There's no information in this data because the outcome of every experiment is random with respect to the previous experiment. We have no idea what our local oscillator was doing, but we now have two regions, and we probe them with the same laser at the same time, and you can see that there's some correlations here, but it's kind of hard to make out this way. So again, we turn to Holger and the atom interferometry community for inspiration. We can plot this data a different way. We can look at the excitation fraction of region 1 on the x-axis versus excitation fraction of region 2 on the y-axis. So we're just plotting the outcomes of the two experiments parametrically now. And now when we plot exactly the same data as it comes in, we can see just how correlated it really is. It all lies perfectly on this single ellipse, almost perfectly, okay? And what this corresponds to is we're actually just probing two Ramsey fringes that are shifted with respect to each other, but because our laser has a random phase shot to shot, we're randomly sampling these two offset fringes, okay? And so by fitting to this data, we can extract exactly what the phase difference between these two offset fringes is, and that tells us about the detuning between these clocks without being limited at all by our local oscillator anymore. And so now we can go from 100 milliseconds out to 26 seconds of coherence, or even more recently, just in the last, this is actually data from last week from my group, we can go out to 75 seconds or so. So we're comparing two different clouds of atoms, each of which are processing or accumulating phase at 400 terahertz. And we can compare them for 70 seconds and they still basically stay in phase with each other, which is really pretty amazing. And it allows us to very precisely measure the frequency difference between these clouds. That's what you see here. So I've shown you in the Allen deviation plots before. Now we're averaging down at 7 times 10 to the minus 18 per root hertz. So just to compare to where we were at before we were at 6 times 10 to the minus 15, now we're at 7 times 10 to the minus 18. So before it took us 114 years to average down to 10 to the minus 19, now it takes us 1.5 hours. And that's an experiment I can convince my grad students to do with a little bit of encouragement. And just to make the connection back to this Moss-Bauer spectroscopy, actually we're back to the same situation we were in before. We're actually not learning about what the frequency of the laser is at all. We're just learning about the frequency difference between these two clouds without worrying about the frequency of the radiation at all. So you can't use this to make a clock anymore, but you can use this to make very precise clock comparisons. Okay. We can do one trick that you can't do in Moss-Bauer spectroscopy, which is we don't have to stop at just two clocks. So here I'm showing we can load as many clocks as we want and make kind of miniature clock network or an array of clocks. And this is very nice because now we can do comparisons between all of these simultaneously. And so if you think about, say, 5 clocks in a linear array like this, if you measure them all simultaneously with the same clock laser, you get 5 choose 2 or 10 of these comparisons all coming out at once. And this is now giving you information about the redshift between each of these clocks at a bunch of different heights. You can see that here we're measuring at 1 centimeter, and we should be able to see that effect after only 2 minutes of averaging, but we're also getting 4 different pieces of information about the frequency differences between clocks that are separated by 2.5 millimeters. And so now we're all set, and you can see that at 2.5 millimeters, we should only need about 30 minutes of averaging to measure it, so this should be a pretty fast measurement, faster than this talk. But of course, I haven't talked at all, again, about systematics, right? We only talked about the statistical effect. So we have to characterize all of the other things that could give us frequency differences between these plots. So we did that, we went down this list. I'm not gonna go through all of them, but just to highlight one that really plays these plots. These plots are sensitive to electromagnetic radiation, including the black body environment, or in other words, all electromagnetic radiation just from black body radiation from the surrounding walls of the vacuum chamber and everything like that. And of course, these atoms should be basically in the same thermal environment, except for one is closer to one side of the chamber and one other cloud is closer to the other side of the chamber. So you're now sensitive to thermal gradients. And so what we did was heat up one side of the chamber with respect to the other. And you can actually see the slope as a function of separation. And you can see this coefficient here. For our apparatus, we find that you get 4 times 10 to the minus 18 per centimeter per Kelvin. Or in other words, all you need is a quarter of a degree Celsius difference in temperature between the top and bottom of the chamber, and it would look just like a gravitational redshift. which is really pretty amazing. But we can characterize this because we can measure the temperature difference to better precision than that. And we can heat it up much larger to actually measure the effect. So we account for that. We accounted for all of these effects. And the last thing I'll say is we did that blind. So we didn't want to bias ourselves to get the outcome that we expected. So we didn't know the answer while we were doing these measurements. We had an arbitrary offset added here using our data analysis software. And this is actually, when I came and interviewed for this faculty position, this is where we were at with these measurements. We were in the middle of taking the data and we were blind, so we didn't know if they were consistent or not. This is what our data actually looked like when we finished the data run. So this is now after I came and interviewed for this job. We took quite a bit of data, about 14 runs. You can see statistically it all agrees, but you can see we were measuring this value up here, and this is the expected value for the gravitational redshift down here. And we had no idea if it was consistent or not because we were adding this blind. And it was a very nerve-wracking experience to finally decide to unblind. You can only do it once. And I wanted to give you just a little taste of what that was like. So here you can see what the data looks like with this arbitrary blind added. We know it's somewhere in this green region. And when we unblinded it, this is what it looked like. It agrees very nicely, which is a big relief to me. Einstein is right, again, okay? You can see here that actually statistically we're a little bit off, but after accounting for our systematic uncertainty, we're completely consistent with the redshift. Here's what our systematics actually look like. Here's how well we can say that the redshift gradient agrees. Okay, and this is my favorite plot of the whole thing. So you take one thing out of this whole talk. Here we're plotting as a function of height difference, our measured frequency difference between these clocks. And this is the redshift showing up kind of in this plot. And there is the thickness of a penny, right? So we're really now measuring the effects of relativity from differences in height, on the order of a millimeter or the thickness of a penny. I think it's pretty remarkable. And it bodes very well, I think, for starting to use these clocks for relativistic geodesy, although of course we're cheating because our clocks are in exactly the same environment, they're in the same little oscillator and everything. So there's a lot of challenges, but nothing fundamental preventing you from doing the same kind of stuff for relativistic geodesy. The last thing I want to do is give you a little sense of context where this is relative to other tests of relativity and where it's going. So to show you this thing from Pound's notebook again, we're actually testing relativity at about the same level as the original Pound Revcon experiment. You can see on here that here's our experiment. I also want to quickly highlight this other experiment from the group where I did my postdoc that was done kind of simultaneously, although they beat us to it. So they did a measurement with a single cloud. They looked at the gradient across that single extended ensemble. They were actually able to measure the redshift at a millimeter. But a couple of points, they didn't do this blind, and they also did it using this world's best clock laser. And we are doing it with a commercial clock laser, which I think bodes very well for using some of the tricks that we've come up with to using this in real applications and using this in clocks in space. But still, this is a beautiful experiment. So if you look at Pound and Revcon in just 5 years, they went from testing it at a part in 10 to a part in 100. I think it's quite realistic for us to do something similar and to increase our precision and accuracy by a factor of 10 or so in about 5 years. And then I'd really like to think about building a meter scale experiment. So we're actually designing this right now. And at a meter scale, we can really, if we get that level of precision and accuracy, we can really be competitive with the very best limits on tests of relativity using space-based experiments in the lab at just a meter height difference, which I think is really cool. And I will stop there. I have one more thing, but I know I'm totally out of time. So I'm going to move on just to show you, these are the kinds of things that I think we can do aside from tests of relativity, including tests of relativity, with this multiplexed clock apparatus that we built. And I want to acknowledge my group, all the people who worked on this and all the funding agencies that supported it. I also want to mention that I also have another half of my group doing research on nitrogen negatively centered in diamond, which I didn't have the chance to tell you about today. So if you want to hear about that, you can invite me to give another colloquium. But here are the people who worked on the strontium optical clock experiments that I just told you about. I am looking for new grad students, so if you're interested, please get in touch with me, and I will thank you for your attention and take questions.
Wonderful, Shimon. Yeah, questions. There's
tell us more about the dark matter stuff?
Sure. Thanks for the question. So I totally skipped over a lot of this. Let me unskip some slides. Okay, so the idea with the dark matter searches with these clocks is the picture looks something like this, which is that, there's a whole class of dark matter candidates where you can treat dark matter basically like a very massive particle. But then there's another class of light dark matter candidates where the mass is very small of the particular particle of dark matter, and you should really think about it more like a wave, more like a photon or something than like a massive particle. And then you can think about moving through these clouds of dark matter or a field of dark matter that kind of surrounds us. And depending on what assumptions you make about how that dark matter interacts with luminous matter, it might not at all, which basically have no hope of seeing it. But if you make some assumptions that it couples either to the electron or the nucleus of an atom, then as we move through this background field, it should shift the frequency of clocks and of atomic transitions in general. And so then there's a few different ways that you could hope to see this dark matter. You might either look for comparisons between two different atoms that have, or even between two different transitions within a single atom that have different dependencies on basically the fine structure constant, if you want, which is sort of just a stand-in for how this thing is changing the frequencies of these transitions. Or you could do a comparison between your atom and your cavity, but for that you need a very, very stable cavity because the cavity length is constantly changing. Or you can do comparisons between different clocks in different places that are experiencing different parts of this field. And for example, if the field is either oscillating or if it's clunky, then these different clocks will experience different parts of the field at different times. And that's what's shown in that up there. And so we can imagine, for example, using our, especially a meter scale experiment or something like that, and imagine we have these two clocks, and we happen to pass through some clump of dark matter, then first one clock and the other clock will get shifted, and we can do these kind of sequences to hopefully detect those kind of very rapid changes in the frequency of these clock transitions. And if you look at the numbers, especially for kind of reasonable length, like say 10 centimeters as you can see there, we can put pretty good constraints on the coupling of these particular dark matter candidates to luminous matter using these kinds of experiments. So that's the idea.
So do you have a current experiment on this? Or?
Well, our current apparatus, the arm is a little short. They're only separated by a centimeter and moving through these background clouds very quickly. But I think a meter scale experiment or two of these experiments side by side can really have a decent amount of science reach. And so we're designing that experiment now. That's one of the many motivations for building this second generation apparatus.
And what's the distance between your theoretically expected? We don't have
yeah, it depends on the mass, and it depends, yeah, so it depends on what model of dark matter you're talking about. So either the mass gives you some wavelength, and then you want that length scale to be on the order of the wavelength, or, and that is kind of a challenge, or there are these models where you have these clumps or clouds of dark matter, things like cue balls or quark nuggets or things like that, that I don't understand at all, I'm just saying words. Okay, but, and those can have sizes on this scale, like meter scale, things like that, at least in print.
So what's the most optimistic assumption?
Yeah.
How close are you to picking that up in terms
Well,
of
I have no idea how reasonable these candidates are. We can cut into untested parameter space, let's put it like that, but I have no idea, it depends on how strongly you think it couples to matter and whether you think this is a reasonably motivated dark matter candidate or not, which I think. I'm not.
Right, I want to give everyone a chance to answer. So how about this time we go all the way to the back?
Yeah, it was a great talk. I have a quick technical question and a general question. So the question is, do you really get 10 independent measurements by 5 choose 2? Or
Great.
It seems like you're...
Yeah, so it depends what you mean by independent. You're getting 10 measurements, but each measurement, you actually are learning about the frequency differences between each of these clouds. So in that sense, you are doing 10 measurements, but the noise between them is correlated because you had quantum projection noise. And so you measured some number of atoms in up or down in each of those clouds. And of course, it's the same noise across all 10 measurements. So we have to understand the statistics to account for that because there is a covariance there if you want. So they're not 10 truly independent measurements, but they are 10 unique different measurements that are giving you 10 different pieces of information. You just have to know how to interpret it properly, and indeed they're not completely independent. Okay, great question.
Real quick, I was going to ask you,
Yeah.
you mentioned about superpositions of location and things
Yeah.
like that. So can you say something about the quantum nature of relativity? I mean,
Well, that's where we're kind of hoping to go. I skipped over this part at the end because I was running out of time and I don't want to keep you all there. But we really are hoping to enter the regime where we can probe the effects of relativity and on the same scale that we can generate these superpositions. Volker is doing very complementary experiments in parallel where he's creating superpositions of atoms trapped in a lattice for tens of seconds. And all right, I'll show the slides very quickly since he twisted my arm. Okay. Very, very quickly, okay, and feel free to leave anybody who's not interested, okay? But you can look at, all right, 1 second. Let me see if I can find it, if not, we'll just do it.
Does anyone have a super quick question while they look at the slides? Super quick. It's less quick.
What if you choose to use strontium instead of other atoms?
That's a great question. So we want an atom with 2 valence electrons to have these narrow intercombination lines. Strontium has a number of nice features in terms of the wavelengths of the transitions that we use for laser cooling and trapping and things like that. But there are other atoms. And also, I was talking to Dan, for example, about his experiments with titanium. There's more complex atoms that also should have nice clock transitions as well. So mostly because it's kind of a well-developed system that we understand very well, I would say. But there's no reason why we can't do these experiments with other kinds of atoms. Okay, so to answer your question, Mike, I introduced this idea of that you could get which path information, or the atoms would have which path information from the gravitational redshift itself. If you plug in the numbers for the experiments that we did, where our atoms, we have different atoms, they were not in superposition, but imagine that it was one cloud of atoms that had been split in 2 and held at a centimeter height difference for 10 seconds. Actually, the frequency difference that we're measuring corresponds to a phase difference of 10 seconds with only 27 milliradians. And what that means is really from like nature's perspective, these atoms are in very similar states. They don't have very much rich path information, and so the visibility of your interference fringes would not change very much. It would still be 0.9999. And I think we can ask Volker, but I think that's it's hard to probably measure a visibility of difference of 0.99. So what you actually need to see something, you can plug in the numbers. If you held atoms at a meter for 10 seconds or 11 seconds in Earth's gravity, then you get a visibility of 0. So you need to be in a superposition of differences in height on the order of the meter for time scales on the order of 10 seconds, at least for strontium, to see a significant change in visibility. And that's a really hard experiment, but it's a direction that I think I'm interested in heading, and I'm hoping to get Ms. Holder to kind of help me do it. So
We should put that in the same vacuum chamber. Other questions? Over there. Yeah.
Yeah, I'm afraid I'm going to ask you to find the slide again, but we showed the chart of the systematics from the optical clock. There were 2 separate characterizations there, and the shifts, the differences in the shifts between the 2 characterizations are not covered by the uncertainty. So what's the difference between those 2 characterizations?
Yeah, that's a great question. You're very observant. Let me pull that up. I apologize. So that was, again, not work that I was directly involved in, although I'm quite familiar with it, so I can tell you about it. So, so these were 2 different, 2 different evaluations with, and in particular, the biggest change is probably from the Zeeman effect, or it should be, and then also from the AC Stark shifts, okay? And so Zeeman effects is magnetic field uncertainty, basically, and there, if you apply a different magnetic field, then you have a different shift, but your uncertainty, typically, it should be pretty much unchanged, okay? But then the other big difference is the AC Stark effect, which you can see that's what they shrank significantly, the magnitude of it, and also the uncertainty. And that was because they actually figured out that they weren't really operating at the true magic wavelength, okay? There's a scalar, vector, and tensor AC stark shift, and they were operating at the location where the scalar shift is 0, and the vector shift should also be 0, but then there was still a tensor shift that was non-zero. They realized that there was a different frequency that they could operate at where the scalar and tensor cancel. So actually you have both the scalar and tensor shift, but at that frequency, those two cancel for a given hyperfine condition. And when they moved there, they had much less uncertainty from the AC stark shift. It's very good.
Thanks for wonderful questions. More now. Going once, going twice. Okay, last question.
I just wonder, why don't you think about the systematic error of, so the Earth is self-spinning, and if you put two atoms, and the system is spinning, it has some effect.
Yeah, that's a great question. So we wrap the Earth's gravity with a little g that accounts for both the sort of centrifugal, if you want, force and the Earth's gravity. You're right, those are actually not exactly equivalent, but from the equivalence principle, you can argue that they are. And then we're just doing an expansion for small changes in height, where the only thing that matters is the acceleration due to gravity that includes both of those terms that we actually measure very precisely with the gravimeter. So we actually just drop something and see how fast it falls. And that's the only thing that we're sensitive to, but it includes both of those contributions, the actual force of gravity and the effect of Earth's rotation, which you can treat like a force if you want or an accelerator. It's a very good question.
Okay, this is Beetle's last one now.
At what point will we be able to measure perturbations from other planets on Earth?
Okay, so these measurements are actually really, really bad measurements of gravity. If you think about it, we have to work extremely hard to see that there was gravity in the lab at all using this technique. And it would have been very easy to just let go of the atoms and watch them fall, and we could have measured gravity much better. So this is not a good way to measure the potentials, from other planets or really anything else, because we're really dominated by the potential from Earth, and we're only measuring it using these relativistic effects. Holger makes much better measurements of gravity using atom interferometry, but as we discussed before, I think these kinds of experiments are starting to merge with each other, and we can start thinking about hybrid versions of these experiments, where we can be sensitive to either gravity itself or the relativistic effects of gravity and things like that. So I think that's a very rich area to explore, but this would not be a good way to see the effects of planets or even the tides or anything else like that. We're really only sensitive to the gravitational potential from Earth, which dominates everything else.
I think it's time to thank Shimon for wonderful